Hey students, welcome back. This is Torah's Elbow Bump. How are you? Are you doing okay? Is your family okay? Remember, if you need anything, send me an email so that I can try to help in some way. So lucky you get to hear my voice again for another lecture. But the best part is we'll be talking more about z-scores, and today we're going to start working with QQ plots. So while we start, to get us started, I just want to look at a couple examples from yesterday. And just remember that when we're working with the normal curve, and remember if the when we're working with the normal curve and you have enough evidence to determine that the curve is actually normal, then you can apply the empirical rule to it, which states that 68% of all values will exist within one standard deviation before and after the mean. Approximately 95% of all values will exist within two standard deviations before and after the mean, and approximately 99% of all values will exist within three standard deviations before and after the mean. Now, these are approximations. We're going to actually start getting into more precise cuts either by the end of this class or the beginning of next class. But the big takeaway, as I said the last class, is that you have to have some amount of certainty that the curve is normal for these proportions to be applied. So to get us started, I have a question here. It says the mean rate of violent crime in the West was 406 per 100,000 people, and the standard deviation was 177. Assume the distribution is approximately unimodal and symmetric. So here, the person that wrote the question is actually saying you should just assume normality. Okay, then they want to know between which two values would you expect to find 95% of the violent crime rates? Between which two values would you expect to find about 68% of the violent crime rates? If in a Western state had a violent crime rate of 586 crimes per 1,000 people, would you consider this to be unusual? And would 30 crimes per 100,000 people be unusual? So let's go over to my Ziteboard. I'm going to get out of here, and I'm going to go ahead and take a look here. Actually, let me see if I can move this over here. Open up our Ziteboard. And let's see if I can actually bring that same question over here. Let's see what will happen if I try to bring it over. Will it show up? I'll just cut paste everything over. Copy. Hopefully this works. Paste. And here are the rest of the questions. Copy. Paste. Okay. Don't know how to move that, but it doesn't really matter. Okay, so I'm going to scooch this over here so we have all the information. Okay, so the mean rate of crime. Okay, so let me just start this by going ahead and just pulling over a blank curve. And this way we can start to fill this out. Like I said, you can do this a variety of ways. Personally, I like to just, when it's something that's pretty straightforward, I just assume draw it in here and see what happens. Okay, so as we know, and I've got blue pen. Okay, so here are our z-scores. So here's 0, +1, +2, -1, -2, and we can even make one way the heck out here that's 3 and -3. And as a reminder, these go out indefinitely. These are our z-scores. I'm going to go ahead and just, to make everything uniform, fill these in. These are positives. These are our z-scores, standardized z-scores. Okay. And then I'm going to go ahead and make a line down here for our raw scores. So I'm going to go ahead and just make a line right over here for our raw scores. These are going to be theoretical raw scores. Okay, so here we have the mean is 406, 406. Standard deviation is 177. So I can actually just use a calculator to figure this out. Let's see what happens if I just put up my calculator here. Did it pop up? Ah, there he is. Okay, let's see. So I've got 406 here, and let's just go to the right first, plus 177 equals, and I get 583. So I could put 583 right here. I'm going to try to write nice and tiny. Okay, and then I'm going to add another 177, right? So plus 177 equals 760. And then I'm going to add another 177, so plus 177 equals 397. That's not 397, what was it? 937. What am I thinking? 937. Okay? And then I can fill in stuff going in the opposite direction by taking 406 and subtracting 177, and I get, no, that did not come out right. What did I put in? Oh, 406 minus 177 equals, that's much better, 229. And then I can subtract another 177 minus 177, enter, 52. And then I'm going to get in the negatives, and there can't be negative people. So again, you just want to make sure that how these things work out, you have something that makes sense. I'm going to go ahead and just put in the negative number, but keep in mind you can't have negative people, so we're just putting this kind of like for reference in case they ask us anything that goes beyond positive 52 that goes into this area. Okay, very good. So here we have our raw scores. So the first question asks, between which two values would you expect to find 95% of violent crime rates? Okay, so 95, well, I'm going to go ahead and put my percentages in here, and actually I can also put in this guy. There. Okay, so here is between one standard deviation is 68% of the values. So the first question, or this question right here, between which two values would you expect to find 68% of violent crimes? It would be between this number, the 229, and the 583. So this would be about 68% of violent crimes. So the question to number one, I would write that 68% of violent crimes are within 229 and 583. Okay, so those were the two. Okay, so now let's go to the top one, which I accidentally skipped. It says between which two values would you expect to find 95% of violent crime rates? So that would be between 52 violent crimes and 760 violent crimes. So 95%, oops, click the button, sorry, of violent crimes are between what did I say? 52 and 760. All right. If a Western state had a violent crime rate of 584 crimes, so 584, right around here, right? Very close to here. Would you consider this unusual? No, I would not consider this unusual because it's just a little bit further than the mean. It's not too far, right? This is not too far. If it was all the way out here or even out here, it would be maybe unusual. But this is not at all unusual, so I'm going to put no. 584 crimes is not unusual. Oops. And would 30 crimes per 1,000 be considered unusual? 30 crimes is going to be like right around here. So that's pretty far away from the mean. So yes, 30 crimes would be unusual. 30. It's unusually low. Okay. So again, we're just setting things up. It says, you could work this out using the modifying the z-score formula. Definitely could do it that way. If it's something just really straightforward where you can just line it up with the curve, you can do it this way too. Okay, so let's go back to our lesson. All right, so let's move this back. Come on, little guy. Let's move back and present. Okay. All right. So here it is. Same kind of thing. We've already sort of set this up. We decided to, create this together. Exact same thing that we did on the Ziteboard. Everything's about the same. It's just written out in different ways. So like right here, what I did was I subtracted twice, but here what they did is they took 406, they took 177 multiplied by 2 and then subtracted it from the 406, which is the same as subtracting it twice. Same thing happened here, but in the opposite direction. Here they multiplied 2 times 177 and added that amount to 406, which is the same as adding 177 2 times, which is the way that I just happened to do it. I really like, one of the reasons why I like working it out with the normal curve is because I can just kind of see it, everything from reference. And if I ever have to look back at it for any other reason, I've already kind of written it out. So here's our answers. Violent crime rates are between 52 and 760. 68% of the values are going to be between 52 and 229 and 583. Nope, because this is within two standard deviations. Yes, because it's very far away from the mean. Okay, so just review on how we can find what I like to call anchor z-scores. They're the ones that we work with the most. They're just nice little benchmarks in order to sort of like keep everything straight. And remember that the normal model, this will only work, those proportions will only be true if the model is normal, if the distribution of the data is normal, meaning that it's unimodal, it's about symmetrical, it has like a bell-shaped curve. And one other thing that I should mention is another way to refer to the normal distribution is the Gaussian curve. Okay. What you'll also see is a type of notation here for the normal distribution. So I'm gonna see if I can use this pointer. Can you see this? Hopefully you can. Doesn't it look like a comet or something? So right here, see where it says n parenthesis 6, 2. It's got like this big N, which maybe you're used to seeing it as like the population. But when you see the big N with a parenthesis and then a number, a comma, another number, and close parentheses, what this is saying is it's a notation that the big N means that the curve is normal. the first number is the mean and the second number is a standard deviation. So I could give you something like this where it says, you know, this is, you have a normal curve with this information, or you have data that has this information. What are percentages within, or what values are within 68% of the curve, okay? So what we're going to start doing now is we're going to look at a couple more figures where we're looking for the probability under the curve, or the area under the curve, and just kind of breaking it up. And then I want to start looking at what that means when we start breaking it up into even more tiny pieces. So let's see. Let me go ahead and pause. Okay, so here we have a cute, really super cute example. Okay, so this is talking about the weights of adorable fluffy kittens. And it's saying that the weight is normally distributed with a mean of 3.6 pounds and a standard deviation of 0.4 pounds. So first off, saying that it's normally distributed tells us we can use the normal curve. The mean is 3.6, standard deviation is 0.4. So I'm going to go ahead and write this down here. The mean is 3.6, and the standard deviation is 0.4. Okay, so if I'm going in this direction, I'm going to add 0.4. I've got 4.0, 4.4, and 4.8. And if I'm going in the other direction, I've got 0.2. I've got 2.8 and 2.4. Okay, and these are my, these are my raw scores. My theoretical raw scores. Okay, so it says, what percent of adorable fluffy kittens weigh between 2.8 pounds and 4.8 pounds? So 2.8 pounds is here. So I'm going to go ahead and draw a line right here. Man, that's an ugly line. I'm off today. Okay, and 4.8 right here. And I forgot to move over my little cheat sheet with all my numbers in here. Wait for that thing to load. I've got a new computer coming. I'm so excited because it's just going to let me fly through things. But I got to make it 4 more days until it gets here. Why is dropping blocked? Why is dropping blocked? Oh, there it goes. Okay. Okay, so here's my little cheat sheet that has everything on it. So I'm going to go from -2 right here to +3. Just to make my eyes, give my eyes a little bit of a break, I'm going to go ahead and come here. And I'm going to go ahead and write in the percentages. So this is going to be, I'm not going to write the percent sign. I'm just going to write 34, 34. This is 13.5, 2.0, 0.5, 13.5, 2.0, 0.5. Okay, very good. All right, so I've got to add from here to here. So what for this one, this and let's go ahead and number these. Question number 1, 2, 3, 4. For question number 1, I'm going to add up 13.5 plus 34 plus 34 plus 13.5 plus 2.0. And if I get my little handy dandy calculator here, and I add this up, I'm going to have, let's see, clear, 13.5 plus 34 plus 34 plus 13.5 plus 2 equals 30. That's wrong. What? What did I do? Okay. I'm going to add this up in my handy dandy calculator. So it's 13.5. Oh, that's what's happening. All right. So I'm going to add this up with my calculator. 13.5 plus 34 plus 34 plus 13.5 plus 2 equals 97. So I have 97%. So 97% of the kitties will weigh this much. Come on. 97%. Okay, this next one says, what percent of adorable fluffy kittens will weigh less than 2.4 pounds? So I'm going to do this one in blue. So here is 2.4 pounds, and I want everything in this direction because I want everything that's less. The only thing that's less is this 0.5%. So this is super easy. This one's just 0.5%. So you see how, like, I just took the time to make myself the curve and I just can go back to it several times. I've just found that works best for me. If it doesn't work for you, that's cool. You don't have to use it. Okay, this next one, I'll do this next one in red. It says, what percent of adorable fluffy kittens weigh between 2.4 pounds, which was here, right, and 4.0 pounds, which is here. So I'm going ahead and adding up the following. I'm going to add up 34 plus 34 plus 13.5 plus 2. Oops, plus 2. So let me get my calculator. Clear. 34 plus 34 plus 13.5 plus 2 equals 83.5. So 83.5% of kitties will weigh between, what is that, 2.4 and 4. And which ones will weigh more than 4.8 pounds? Let me do this one in, oh, we haven't used orange, so I'll use orange. Here's 4.8, and I want everything that's more, so I'm going to go everything over here. It's just going to be 0.5%, 0.5%. Okay? So you should be able to add up the different pieces. If we're looking at notation, what this might look like would be, let me see if I can just pause this. I'm gonna rewrite these a little bit further down because I want you to see what the notation would look like for all of this. So I'm gonna write the notation of something you might see for each one of these kind of off to the side. Let's see. So for this one right here, I could see this one, the information for this question being given to you like this. So it'd be like capital N, parenthesis, 3.6, comma, 0.4, close parenthesis. For the percent of adorable fluffy kittens that weigh between 2.8 and 4.8, you might see something given to you like this. It might be like, what is the proportion of kittens that are between 2.8 and 4.8? For the second one that we did in blue, what percent of adorable fluffy kittens would weigh less than 2.4% or 2.4 pounds? Would be like, what proportion of kittens weigh less than 2.4 pounds, sorry, 2.4 pounds. For the one in red, it would be what proportion of kittens weigh between 2.4 and 4. And for the last one that is orange, it would be like what proportion of kittens are greater than, weigh more than 4.8 pounds. So these are all corresponding here to the colors. So I just wanted to make sure that I had a moment to kind of talk over the notation that you would see, that you could see. Sometimes I might write it like just with the words. Sometimes you might write it with the notation. You should be able to read it either way. Okay, so we've had a little bit of practice of working with the anchor z-scores. So I'm going to go ahead and put in the information for a curve here. This should be one that might look familiar to you. Think where you have seen this information before. I've gone ahead and written it as a notation, as like just a normal notation. So this big N right here is telling you have a normal curve. The mean is 100 and the standard deviation is 15. And here I have a normal curve with my deviations already marked, and the z-scores are right here. So I'm going to go ahead and draw a line down here, and using the information, I'm just going to go ahead and fill out my info. So here's 100, 115, 130, 145, 85, 70, and 55. Perfect. Okay. So here are my theoretical raw scores. So here I'm going to pull over this example right here of this Google sheet. And what I've done here is I've got my different z-scores right here. I just happened to go, I'm going to make this just a little bit bigger if I can. How can I make this just a little bit bigger? Okay. What I've done here is I've just gone ahead and used the mean as 100, standard deviation is 15, and what I've done is I've gone ahead and I've calculated all the theoretical raw scores from everything from -4 all the way to +4. Okay. And just to give it a double check it, let's look at some of the ones that we already did. Well, we started with the mean as 100, and then when we added 15 and went to 1, we've got 115, and here is 130, and here is 3, and here is 4 if I were to keep on going. And the same thing happened in the opposite direction, where 1 standard deviation less than the mean would be 85, and 2 less would be 70, and 3 less would be 55. And if I kept on going, there would be 4 standard deviations would have a theoretical raw score of 40. Okay, now what this has done using the z-score, we basically just plugged it into the z-score formula that we shared before and created this relationship. And I'm going to go ahead and plot the z-scores on the x-axis and the theoretical raw scores on the y-axis, and what you'll see is that you have this perfect one-to-one relationship, right? Everything's perfectly within a line. It's perfectly lining up, okay, with that, how can I say this? Because the values are evenly spaced, or the z-scores are evenly spaced, we were working with theoretical raw scores, not real raw scores. You're going to have this perfect relationship, this perfect relationship that's calibrated with the mean and the standard deviation. But we don't usually have perfect data. We really usually have with random messy data, and it's not going to fit perfectly against this line. So one thing that we can do in order to check to see if our data is normal is to check how well do our raw scores compare to the theoretical raw scores. Let me say that one more time. We're going to see how well real data compares to the theoretical raw scores that would have occurred if this thing was perfectly normal. Perfectly normal, no skew whatsoever. Remember, raw data will have some skewness, some kurtosis. It can't be perfect. When it's too perfect, that's when it starts to look kind of like it's fake. Like something must be wrong. Nothing can be random that is this perfect. So that's when we start to use the QQ plots. And what the QQ plot does is it takes the mean and the standard deviation, and it calculates the perfect theoretical raw scores if your data was normal, perfectly normal. And it plots it against a scatter plot of the real raw scores for your real data that is not normal. And it kind of looks like this. So I'm going to go ahead and go over here to some data that I have saved. And this is some science achievement data, just to give you some background of what it is. Okay, let's look at the summary statistics, okay, to see how this works. So let's just check for normality again. So I've got an N of 500, pretty good N. Let's see, I've got the mean is 5.9 and the median is 5.7, almost, right? So the mean is slightly lower than the median, kind of a left skew. Slight left skew, not very much at all. Doesn't show up here. This shows up that it's almost perfect, 0.04. So it shows that if anything, it's just very, very, very slightly positive. Okay, kurtosis is 1.33. It's within the acceptable range of positive and negative 3. So the numerical calculations look promising. Let's look at the histogram. Here is the normal curve. It's got this outlier all the way out here, which is probably what's causing it to be a little bit more positive, but it's not messing it up too much. It's just got that one outlier. We can also see it out here. The mean and the median are close to the middle of the mode. The median is the median is the red one. The median is pretty much in the center of the H spread. The left whisker is slightly longer than the right whisker, which makes sense because we had, that's what we saw originally. So there is some indication that this is good to go. Okay, it's not perfectly normal. If it was perfectly normal, it'd have zero skewness, zero kurtosis. It doesn't. The mean and the median would be exactly the same. They're not, but they're close enough. Okay, we're looking for close enough for this to work. That's why we have the range of positive and negative 1 for skewness and the range of positive and negative 3 for kurtosis. So another thing that I can do to check again to see if my data is okay is by using a QQ plot. And the QQ plot is, I'm going to go ahead and make it here, is going to plot my theoretical raw scores, right? Theoretically, if my data was perfect, on a line, and then it's going to show the scatter plot of what my data actually is doing on top. So I'm going to compute it, and this is what I get. Okay, this red line right here is my perfect theoretical raw scores. Okay, you can see that pretty much the scatter plot is pretty much right on top of it. At the end here, it gets a little bit farther away. Over here, it gets a little bit farther away. We've got these two outliers way up here, but for the most part, it's hugging the line of regression. So this would be an example of what a QQ plot would look like for something that also gives us evidence of normality. That really, except for the extremes, except for the very ends, the very low values here next to -3, and the very high values here next to between +2 and +3, there's a little bit of deviation from the line. It moves away from the line, but other than that, it looks pretty good. So this is the way the QQ plot works. It's just to check to see how are the raw scores kind of lining up with the theoretical raw scores, and you really just want some level of some level of distance, I guess. If you see that the points are pretty much hugging this line except for down here and up here, again, another indication that your data is suitable for statistical use. Okay, so now when we start to do our data analysis and checking for normality, we're also going to be looking at QQ plots. So let's review all the things we can do to check for normality. Number one, you can check to see what the relationship is between the mean and the median. Number two, you can see what the skewness is. The skewness value should be between +1 and -1. Number three, you can look to see what is the relationship, what is the kurtosis value. The kurtosis value should be between +and -3. You should be able to look at the histogram, see if it's unimodal, the mean and the median are within the center of the curve, and there's no extremes on either side of the tails. The tails are approximately equal length. Look at the box plot to see if the median is in the middle of the H-spread and the whiskers are approximately equal length. And then now you can look at the QQ plot to see that the center values that are closest to the 0 z-score are hugging the line of regression, or the theoretical raw score line, and just the ends, the very low values on the z-scores, the higher values of the z-scores start to move away from the theoretical raw score line. Okay, so I have the same looking at this same example, going back to it, we have our z-scores, right, in the first line that are stable. We've got our theoretical raw scores, and that is what we used, what actually QQ plots use to find the theoretical raw scores, and then the QQ plot also plots the real data scores on top of it, so that you can judge how far is your data away from what should happen, as opposed, like, how far is it from what you should expect to see. So now let's start talking about what happens when we start breaking this up into even smaller pieces. So let's say I don't want to find the probability between two anchor z-scores. Let's say I want to find the probability, like maybe from here to here. I want to find this area under the normal curve. And it's not something that I can necessarily judge. I don't know what that is. Okay, I want to find, or maybe I want to find how much is to the right of this or to the left of this. For any other numbers besides the theoretical raw scores, you're going to have to either rely on a z-table, which is, let me just tell you, it's a pain to use, or technology, which is okay to use. So let's start looking at some ways that we can start using technology in order to help us find the probabilities under the normal curve when we happen to know z-scores. So for that, you're going to go into ePortfolio. And if you go into ePortfolio, you'll see this area that says Statistical Tools right here. And when you click on Statistical Tools, you can go down to where it says Probability Information. And then, oops, what did I do? Probability Information. And then you'll see this hot pink one that has already been highlighted for you. And you're going to click on that one, and it's going to download an Excel file called Normal Distribution XLS. All right. So when I open up the normal distribution, or actually it's called Normal Distribution Modified. Okay, and you'll see, just like all the other spreadsheets that are on ePortfolio, you always have to enable the editing. So I'm going to go ahead and click on Enable Editing. So what this will help you do is it will help you find the areas to the left, to the right of the z-score. It will help you find a z-score, you know, various things. It might even, it does quite a few calculations for you. Just like in the beta count analysis, you're just going to use the bright yellow boxes. If you change any of the other boxes, this sheet will stop working and you'll have to close it out and reopen a new one. At any time that you feel that your calculations are, something's wrong with them, always go back into ePortfolio and open up this probability curve again. Okay, so let's just say here I want to find the probability to the right of one of my anchor z-scores. Okay, so let me see. I'm going to go ahead and let me pop this guy up real quick. Let's say I want to find everything to the right of 115, to the right of positive 1 z-score. I can go into my thing here and I can put in z-score positive 1, enter, and it'll tell me that there's approximately 84% to the left of it and approximately 16% to the right of it. Notice that these numbers are they go out many decimals. This is another situation where the computer is trying to help you reduce error. It's going out many places, many place value places to the right so that it maintains a certain amount of precision, and you're compounding less error later. So remember when I told you that the distribution is an estimation. The 68, the 95, the 99, that's an approximation. It is not precise. Now we're going to start getting into more precision and being more precise in order to continue trying to reduce error. So here we have everything to the left would be 84% and everything to the right would be 16%. I can also look for things in between two z-scores. So let's say I want to find the amount between two standard deviations before and after the mean. Oops. So I'm going to put positive 2 and negative 2. Okay, in this area it says between two z-scores. Here's my larger z-score is 2 and my smaller z-score is negative 2. And when I look to see what is in between, 95.44997736%. Okay, this is written as a decimal, so remember you're just going to move the decimal point over 2 times to get the percentage, or multiply by 100. But basically what you're doing here is you've got what's in between these two z-scores, and right here you have what is outside those two z-scores. Also, if I wanted to see what my probability is when I have the mean, the standard deviation, and one of the raw scores, I can put that here. So using my example, I can use 100 is my mean, my standard deviation is 15, and I'm going to say that my value, I'm going to say I have 130 IQ. I'm looking for what's happening when I've got 130 IQ. Well, to the left of the z-score, there is approximately 98% of the values exist to the left of the z-score, and approximately 2% of the values exist to the right of the z-score. Okay, this can also give you what's happening with if you've got the mean and the standard deviation, and you want to know what the raw score is for a theoretical z-score. I'm going to put in a raw score of -1. I should get 85, and boom, I get 85. So this is kind of nice because it tells you exactly what's happening throughout. It does the calculations for you very quickly and easily. And then if we have something that is much more precise, like, so for example, I want to know what percentage of values are to the right of -1.278 z-score, it does the calculation for me. Whereas if I were using the empirical rule, I wouldn't be able to do that. So let's look at some examples and see if we can use our little machine to help us out. Let's go to here. Okay, we'll do this baby seals. Little baby seals. Okay, and make sure that can I drag this over? Yeah, I can. Okay, so it says research has shown that the mean length of a newborn Pacific Harbor seal is 29.5 inches and that the standard deviation is 1.2 inches. Suppose that the lengths follow the normal model. So we know we're using the normal curve. So that means we can use this little machine. Find the probability that a randomly selected pup will be more than 32 inches. Okay, so first things first, I've got the mean, the standard deviation, and I have one of the values, one of the x's. Okay, so here I've got the mean. I can use this guy right here. And what did it say the mean was? The mean was 29.5. So 29.5. The standard deviation was 1.2. So I'm going to put 1.2 here in the standard deviation. I want to know how the pup will weigh more than 32 inches or something. There'd be 32 pounds. I don't know. Okay, and let's see what I've got. It says, find the probability that a randomly selected pup will be more than 32 inches. So the probability that the pup will be more than 32 inches, if I look at the normal curve, more would be going to the right. Answer, the numbers get greater, you have more as you go to the right. So then you would have 0.0186 as your amount. And is that what they got too? They got 0.19. So what they did is they just rounded to the thousandths. So 0.186 is the same as 0.19. So they just rounded it. And if you see here, they just used StatCrunch for this instead, and they got the same answer. So this got rounded. All right, so let's do a couple more practice, a little bit more practice with the machine. So here I have a normal curve. The standard deviation is 1, the mean is 4. And the first question I ask is, what is the probability of a z-score being between 2.7 and 3? So it's not asking about the theoretical raw scores, it's asking about the z-scores. So a z-score is 2.7. 2.7 is probably right about here, and 3 is right about here. So it's wanting to know what is the area underneath that curve. Tiny area. We should get a very small number. So for that, I can go over to my little handy dandy computer. And here I want to find the area between two z-scores. And I need those two z-scores. My two z-scores are, if you want to take another look, I'm looking between 2.7 and 3. Okay, so I'm going to come over here to my calculator. I'm going to put 3 as my larger z-score. And I'm going to put 2.7 as the smaller one. And then I'm going to scroll down a little bit to where it says in between large and small z-scores. And you'll see that it has 0.002 or 0.2%. So the probability of something happening between these two z-scores is 0.2%. Or if I were going to write that as a decimal, I could write it as 0.002, right? This is a percent way to write it, and this is the other way, is the decimal way to write it. Let's see if I wanted to go ahead, and I'll do this one in blue. Let's say I wanted to see what is the probability of a z-score being greater than negative 1.173. I just want to know what is the probability of a z-score being greater than 1.73. I can pop up this guy again, and let's see what I've got. Here I've got z-scores. I'm going to go ahead and put in, and it's going to tell me the left and the right. So I'm going to go ahead and put in the number, which was 1.173. Was it negative or positive? I can never remember. Negative. Negative 1.173. And I want to know what is greater than that. So everything greater than that is going to be to the right. So this would be my number. The number would be 0.879 0.6. So if I wanted to round this, I could just say it's 0.88. So 88% or 0.88. And I could write that here. 88% or 0.88. Okay. What if I wanted, I'll do one in green because I haven't used that one yet. What if I wanted to find the probability of a z-score being less than negative 2.14? Okay. Just go right here, back to my table. I want it to the left, so negative 2.14. This time I want it smaller than this number, so I'm going to look to the left, and the answer is 0.16. One seven, I guess. Depends on how I want to round, and this would be the same as 16% or 16.17%, depending on how you round it. Let's go ahead and see if we can just make it a habit of at least rounding to the hundredths, unless you have something that can only be expressed as a thousandths, just not to get too crazy. Okay. So that's how you would use. So basically, what have we done here? We've used, of this normal distribution calculator, you can use the z-score when you can find the areas to the left and to the right of the one particular z-score. You can find the areas between two z-scores. You just put the larger z-score here and the smaller z-score here. If you've got the mean, the standard deviation, and a raw score, you can also find the area to the left and to the right. And we will start to use these other two sections in another lesson. So let's see, what is today's big idea? So today's big idea continues to be that when the distribution of the data is normal, you can predict the probability of an event. We depend a lot on making sure that our data is normal. So another way that we can check normality and check for the assumption of normality is by using a QQ plot. A QQ plot works when theoretical raw scores for a perfect normal curve are created using the standard deviation and the mean. And these scores are plotted against z-scores on a graph. It creates a perfect line. The real raw scores are then plotted against this theoretical line. So they'll be a little bit off because they're real raw scores. They're not perfect. They'll be real data has some degree of skewness and some degree of kurtosis always. Therefore, if the real data hugs the theoretical line, this is further evidence that the data is normal. It's not much different than a regular normal line. If we just had to calculate areas between anchor z-scores, we could just use the empirical rule. The empirical rule states that approximately 68% of all of the data will fall within one standard deviation before and after the mean. 95% of all data will fall within two standard deviations before and after the mean. And 99% of all data would fall between 3 standard deviations before and after the mean. Okay. However, the area under the normal curve can be divided into many, an infinite amount of sections. In order to calculate these fragmented sections, then you're going to have to depend on either a z-table, which is kind of a pain to use, or technology, which is what we're going to use for this class. So that's it for today. The big idea is make sure your data is normal so that you can apply the probabilities as needed. When you get into using z-scores or probabilities that are not actually hitting exactly where the anchor z-scores exist, and you start getting into those little spaces in between and cutting up those little spaces in between, that's when you're going to need to rely on technology. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay? This is your teacher, Torres, saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!